Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And this is the fourth continuation of our lecture called A Gentle Introduction to Differential Equation Series Solutions. Recall we spent several videos talking about ordinary points, and we knew that we could have a infinite series, in fact a power series solution to those under the assumptions that we make here. But if a point's not an ordinary point, we call it a singular point, and that's what we're talking about today. So in this section we begin to study series solutions of a homogeneous linear second order differential equation with a regular single point x0 equal 0, and it can be written this way, where a of x, b of x, and c of x are polynomials, and a of 0 does not equal to 0. Now we will see as this theory unfolds that there will always be at least one solution, and it will be of this form. It will be x to the r times the summation n equals 0 to infinity of a n x to the n, where a0 doesn't equal 0 and r is a number to be chosen later. Now please note this is not a power series because r is not necessarily an integer. In fact, it's not necessarily a positive integer. So the method we use is called the method of Frobenius. And so the computations don't get unwieldy. We're going to restrict our attention to the case where the a, b, and c functions of polynomials of degree not greater than 2. So that means I have coefficients of alpha going up to a degree 2, coefficients of beta going up to a degree 2, and coefficients of gamma going up to a degree 2. And alpha, beta, and gamma, all those things are constants, and alpha 0 does not equal to 0. And most equations that arise in applications can be written this way. Euler's equation certainly is a simple example of that. Bessel's equation we'll talk a little bit more about soon, but that is an example of that. Laguerre's equation, and even Legendre equation if we modify it slightly. So this is an important topic. Now, let's think back to operators, and we're going to have L of y is going to be the operator that we have. And we're going to be talking about some polynomials here. P0 of r is going to be the polynomial defined this way, but we have alpha 0, which is associated with the constant terms up here, alpha 0, beta 0, and gamma 0. So those are the constants, and that's how r figures in. And this is called the Indiccio polynomial, or Indiccio equation. And this is going to be crucial for us to determine what r is from this. These other two, this one is alpha 1, beta 1, and gamma 1 as coefficients, and those are aligned with the linear terms that we see up here. And P2 of r is alpha 2, beta 2, gamma 2, and those are the coefficients lined up with the squared terms up there. Okay, so those are polynomials that can be derived from this expression, and they're going to play a role in our calculations. We still don't know what r is. But suppose r is a real number such that p0 of n plus r is non-zero for all n, then we have these definitions. Now these are going to be, once we know what r is, these are what the coefficients of part of the expansion, not the x to the r, but the other part, the summation a to the n, x to the n, these are what the coefficients are going to be, but they do depend on r. So this is not a0 times r, this is a0 of r is going to be 1. A1 of R is going to be this relationship, and you see we had to have this to be not 0 because we're dividing by it. And the nth term for n bigger than or equal to is going to be this. You see, this is solving in general for the recursion relationship. Now, you don't have to do it in general. In fact, in the book, Zill doesn't do it that way, but that's the treatment I'm showing you right now. So we have those. And we now have a theorem, and this is representative of the kinds of theorems you'll find about the methods of Frobenius. So let L and those coefficients be as we talked about, and also the p's are as we talked about. And suppose the indicial equation, which is the one that is P0 of R, and we're setting that equal to 0, and it has real roots, R1 and R2. And by the way, even though it says R1 is the bigger one, and that's fine, the two roots really shouldn't be equal in this. So anyway, if we have that, then y1 of x equal x to the R1, where R1 was this first root, times the summation n equals 0 to infinity. This is a sub n found through the recursion relationship, but it's based on the value of R1 times x to the n. And that's one solution. And moreover, if R1 minus R2 is not an integer, that means it's not 0, 1, 2, 3, or plus or minus 1, plus or minus 2. I guess it always has to be positive because we made that one bigger. Isn't an integer, then y2 is going to be x to the R2 times this infinite sum, but the coefficients now depend on R2 is also a solution. And moreover, this is a fundamental set of solutions. That means they're linearly independent. That means every solution is a linear combination of those. Let's do an example. So we want to find a fundamental set of Frobenius solutions for this expression, and we just want to collect the first 6 coefficients. So we look at our indicial polynomial. It is this one. We set it equal to 0. So our roots are going to be minus 3/2 and minus 2, and the difference is not an integer, so we know the solutions are going to look like this. Again, it is not a sub n times minus 3/2, it's a sub n when you put in minus 3/2, and this is a sub n when you put in minus 2. So we run through the equations and we get this, and we say, okay, what happens when r is equal to minus 3/2? I get this. And what happens when r is equal to minus 2? I have this. And so these are my two solutions. If you have only linear terms here and not quadratic terms, the recursion is simplified a great deal. And in fact, you could work a problem. Here's a problem that has only linear terms, and we can get an explicit formula for the coefficients. And so here's our indicial quadratic, and so it's going to be 1/3 and minus 1, and the difference is 4/3. So that's not an integer, so my solutions are going to look like this, and I need to find out what these coefficients are. And so I have this simpler relationship, and I will see what happens when r is 1/3, and I will get this. And by the way, they've used a different notation here. This is instead of a sum, the product is like this. That's the instead of summing, that's the product of those things. And when r is minus 2, we get this. Checking these calculations and doing them yourselves would add much value to your studies. Now, it is more complicated than that because you have different cases. We talked about case 1, but there's case 2 and case 3. And there's also a case where you have things called irregular singular points. But that's a general idea for that section, and we'll continue our discussion of a gentle introduction in 24.5.